So I've set up a little ramp here, and this is an object just rolling down the ramp. The ramp tilts down towards this side, and so I just put something at the top of the ramp, and it rolls down the ramp, and I can just catch it, right? And so I'm going to roll different objects down the ramp, and I'm going to show you that they roll on different rates depending on their shape, right? And so this is a solid sphere, and this is a disk, right? It's a solid cylinder, which is the same thing as a solid disk in terms of its physics. And so we're going to determine which one rolls faster, and we're just going to do it by holding. I'm just going to hold the two objects like this and release them, and you're going to see that the circle. Hopefully, you can see that the circle, that the solid sphere rolls away from the solid disk. So it's faster than the solid disk. Here is a hollow sphere and a solid sphere. The width of them doesn't matter. And so I'm going to do the same thing again. I'm going to put the solid disk in front of the hollow disk, and I'm going to let them roll together and see if this guy can keep up. And you'll see that the solid disk rolls faster. And just in case you're wondering, I'll reverse the order, right? And you'll see that the solid disk will keep up with the hollow disk all the way down. And so objects roll of different shapes, roll at different rates. And it has to do with how potential energy, which they have at the top, is converted into kinetic energy, both in translation and in rotation. And so that's what we're going to talk about next. All right, so this is objects rolling down a hill. So I just gave you kind of a demo of that, and we're just going to look at what happens when an object rolls down a hill. And so this could be a round object, right? And if you remember, if we did for objects sliding down a hill, or this was, for example, a roller coaster, what we're doing here is we start out with potential energy, and then down here we have kinetic energy, right? And so if the object wasn't rolling, we would just say, without friction and no rolling, because it wouldn't roll without friction, but we would say the potential energy at the top plus the kinetic energy at the top is equal to the potential energy at the bottom plus the kinetic energy at the bottom. And so we're looking at the change in potential energy. Well, let's just say it this way. So the potential energy at the top is mgh, if you remember that, right? Where this is how high it is at the top, right? And then we'll call it h top, say, and then h bottom equals 0, and so PE at the bottom is mg h bottom, which is just 0. Sorry, it should be PE, right? The kinetic energy at the top is 0 because it's not moving, and the kinetic energy at the bottom is just 1/2 mv squared. So the potential energy at the bottom and the kinetic energy at the top are both 0, and so what we get here is mg h top is equal to 1/2 mv squared, where this is the v at the bottom, right? The m's cancel, and we got v is equal to the square root of 2g times h, where h is the height of the thing that we're rolling down. So that's without friction. It's with no rolling. When things start to roll, you don't just have the translational kinetic energy, which is what we're talking about here, the 1/2 mv squared. It's moving, sure, it has that kinetic energy, but it's also rolling, and so it has rotational kinetic energy. And so I'm going to redo this problem, but now I'm going to allow for rotational kinetic energy in addition to translational kinetic energy, and we'll see this will look a little different. So now let's look at objects that are actually rolling instead of sliding, right? We'll go to what we were after now. And so I'm going to do the same problem I did a second ago, right? Here's the height that the object starts at. It rolls down to here, and it goes off this way. Its speed here is v. I have v naught equals 0, h bottom equals 0, except now, in addition to sliding, it's also rolling. If I want, I can say omega naught equals 0. And so we'll say the object has mass m and radius r, and I'm gonna switch around, but let's say for now, let's say it's a solid disk, and so I equals 1/2 m r squared, again where r is the radius. Okay, and so we're going to do the same thing we did before. We're going to say, look, the potential energy at the top plus the kinetic energy at the top equals the potential energy at the bottom plus the kinetic energy at the bottom. And again, we can say that the kinetic energy at the top equals 0 because it's not moving, it's stationary at the top. And finally, we're going to say, look, the potential energy at the bottom, which is just mg h bottom, is 0 because that's where we chose the height to be 0. And so that cancels this guy and this guy, and just like before, we have the potential energy at the top is equal to the kinetic energy at the bottom. What's different this time is that now we have kinetic energy for translation plus kinetic energy for rotation, because not only is it sliding like it was on the last slide I did, but it's also rolling, right? And so this is 1/2 mv squared plus 1/2 I omega squared. The left-hand side, the potential energy due to at the top is just mg h top. And so we can use this information to determine the speed at the bottom. So now instead of this equation, we get mg h top, that I use that instead of the potential energy at the top, equals, and so it's 1/2 mv squared plus 1/2 I omega squared. You say, well, there's a lot going on here. Well, remember that this is I is equal to 1/2 m r squared. And so this becomes mg h top equals 1/2 m v squared plus 1/2 times, instead of the I, I'm going to put that there, 1/2 m r squared omega squared. Right, I'm going to have to erase up here just a little bit. And so this becomes mg h top equals 1/2 m v squared plus, so keep an eye on this. This is, a half times a half is a quarter, and so it's 1/4 m r squared omega squared, right? 1/4 m r squared omega squared. This is the potential energy it started with. This is the kinetic energy it ends with because the wheel is moving. This is the kinetic energy for rotation it gets because it's a solid disk and it's rolling at angular velocity omega. Now I want you to remember that for a rolling object, v equals omega r for rolling. So v squared is equal to omega squared r squared. And so I can replace this with v squared, and I get mg h top equals 1/2 m v squared plus 1/4 m v squared, right? this is looking like something that's pretty easy to solve. First of all, the m's cancel, right? And so I get g times h top equals 3/4 v squared, or I get v is equal to the square root of 4/3 g times h top. If you remember, in the last sheet we did, we had the square root of 2gh. The fact that I had to include rolling just changed this coefficient here. The other thing I want you to notice is that suppose instead of being a solid disk, this had been a solid sphere, right? What would be different in this problem? Well, instead of 1/2 mr squared, it would be 2/5 mr squared, because that's what a solid sphere is, it's 2/5. And so this number would be 2/5. I would have a 2/5 here, and so instead of a 1/4 here, I would have 2/10, because 2/5 times 1/2 is 2/10. This would become 7/10 when I added them together, because it would be 5/10 plus 2/10. This would be 7/10, or 10/7. So this is a solid disk. The speed for a solid sphere a couple of things, other things to notice. Notice that this equation does not depend on the radius. So any solid disk will have this speed at the bottom. Any solid sphere will have this speed at the bottom. As long as it's a sphere and it's solid, not only that, the radius doesn't matter. Right? The radius of this thing doesn't appear in this equation. The speed of the disk is this, regardless of its mass and its radius. All it has to be is a solid disk. Same thing here. The speed of the solid sphere just depends on the fact that it's a solid sphere, which gives us this 10/7, and the height, not on the radius or the mass. So I'll do a couple of these with numbers in them here. So once again, we're still doing objects rolling down a hill. Here we're going to be a little more specific and say, look, a solid sphere of mass 2 kilograms and radius 0.4 meters rolls down a hill of vertical height 5 meters. What's its speed at the bottom? And so we just came up with, last time we said it's the square root of 10/7 times gh, where that's the 5 meters. But I'm just going to do it again. I'm going to say, look, the kinetic energy at the top plus the potential energy at the top equals the kinetic energy at the bottom plus the potential energy at the bottom. And we're going to say, look, the height at the bottom is equal to 0. And so since it's got no kinetic energy at the top, assuming it starts from rest at the top, right? It starts from rest here. It's got no potential energy at the bottom. And so this becomes PE at the top is equal to the kinetic energy at the bottom, which is the kinetic energy for translation, plus the kinetic energy for rotation, which is 1/2 mv squared plus 1/2 I omega squared, right? But again, I for a sphere is 2/5 mr squared. And so what we get is mgh top, which is what the potential energy is, that's the formula for potential energy, is equal to 1/2 mv squared plus 1/2 times, instead of I, I'm going to put 2/5 mr squared omega squared, and that's equal to 1/2 mv squared plus, so 2/5 times 1/2 is 1/5, and so I'll say 1/5 m r squared times omega squared is v squared, and so this is equal to 1/5 mv squared. A fifth plus a half, you got to find a common denominator. That's 5/10 plus 2/10 is 7/10 mv squared, and so that gives mgh equals 7/10 mv squared. Again, the m's cancel like they always do, and I could still put that little t there. I get v is equal to the square root of 10/7 times g times the height at the top, which is the square root of 10/7 times 10 meters per second squared times 5 meters. And what I get for that is about 8.5 meters per second. Right? If I wanted to say b, I could say b, what is its angular velocity? Right? And there they're asking us for omega at the bottom, right? And again, since v is equal to omega times r, I get omega is equal to v divided by r, which is 8.5 meters per second divided by 0.4, which is about omega is about 21 radians per second. Slightly more than that. So if this had been a solid disk, it would be this. I would have put in here. I would have put in 1/2 mr squared. If it had been a hollow cylinder, I would have put in a hollow sphere. I would have put in 2/3. If it was a hollow cylinder, I'd put in just mr squared, 1 times mr squared, and so on. You just have to pick the right part of this, and that gives you the right rotational inertia, which then lets you solve for the height, for example.